Good morning. So we are going to be doing the rest of lecture four today. It's not going to take too much time, probably about say like 45 minutes to 15 minutes. We'll go through some of the poll question as well. And that will be it. So last time we were talking about the tonicity. Um, in class. Okay, we talk about how if you put a cell in different solutions, is going to cause water to move differently into and out of the cell, and ultimately that's going to result in the cell changing its shape, changing its volume. So isotonic is a situation where the concentration outside and inside of the cells are balanced. And so there's no net movement. And if we focus on the animal cells for now, we are best placed in an isotonic environment. Our cells are best placed in an isotonic environment. Uh, the hypertonic environment is where the solute concentration is greater on the outside, and so it will draw water out of the cell, causing it to shrink and shrivel up. We call that plasmolysis. And finally, for the hypotonic solution, that's where there are more solute on the inside of the cell, and that's going to draw fluid into the cell, causing it to swell up and ultimately burst if we are talking about an animal cell. And so in the PowerPoint slide, you can see the three different scenarios here illustrated by the red cell. On the left, it's an isotonic environment, so they are in their normal shape. In a hypotonic environment, they swell up. You can't really tell whether this has burst or not yet, but this condition, if it's sustained for some time, it might eventually burst and cause the red cells to die. We talk about the water toxicity, right? If you consume too much water in a short period of time. And finally, on the right side here, we have the hypertonic environment, which again draws the water out of the cell and cause them to shrink. The cell won't die. As soon as you rehydrate, they are going to plump up again, and it's going to be just fine. Okay, so I know many of you are planning to go into a healthcare related career, maybe practical nursing or registered nursing eventually. And a lot of times you might have to prepare or administer intravenous fluid to your patients, okay, which is IV solutions. And depending on the condition of the person, right, depending on what kind of ailment they're having, you might need to give them different kinds of IV solutions. For healthy patients, people who are otherwise healthy, like there's not like special trauma or something like that, then the IV solution is typically isotonic, which makes sense. Okay, if you're gonna give some fluid to a person, you want to give fluid that is similar to what normal cells experience. Okay, so you give them isotonic IV solution. So isotonic IV solution is 0.9% normal saline. Okay? You will learn concentration later on in chemistry. I know I keep on saying that, but you actually will. So 0.9% basically means 0.9 grams of NaCl. Right? NaCl is sodium, as you know, per 100 milliliter of solution. Right? So that percentage is isotonic for our body. Right? So these kind of salines are widely used for rehydration purposes. So if someone is experiencing bleeding, right, hemorrhage is bleeding, vomiting or diarrhea, and they have lost quite a bit of fluid, then you would give them the normal saline to rehydrate. Okay. We can't just tell them to drink water, right? Because if you're losing a lot of fluid and you just drink like regular water, that's going to dilute your blood further, right? Risking the blood condition to become hypotonic, right? So we have to rehydrate with normal saline. And then we have half normal saline. Okay, so half of 0.9 is 0.45%, and this is hypotonic saline. It's lower than what the normal is. So this is used for treating things like hypernatremia. You don't have to memorize these names, okay? Like for the quiz, you don't have to memorize it. Like I'm just showing you some relevance of what we're learning, right? So hyper is too much. Uh, Natrium is sodium, actually. That's why the symbol for sodium is Na and not So, right? And emia means in the blood. So hypernatremia is too much sodium uh, in the blood. Which PowerPoint is this? This is the one we've been doing, the lecture for the same one we've been doing on Thursday, Wednesday, on Wednesday. But it's okay, don't worry about it, because after this slide, we're just going to be taking a note. I'm not going to use the slides anymore. So even if you don't have it, it's fine. Don't worry too much about it. So if a person have too much sodium in their bloodstream, then you want to dilute it for them, okay? So you give them hypotonic saline, right? Or if someone has diabetic ketoacidosis, okay? Diabetic patients sometimes generate a lot of ketones. Okay? Keto here is referring to ketones. Ketones is it's like a group of chemical that has a specific functional group on them. They are usually acidic, and for diabetic patients, sometimes their body metabolize a lot of fat in a short period of time, and that generates a lot of these ketones that will cause the blood to become a little bit of acidic. So you want to flush the system with these hypotonic saline. Finally, we have a 3%, that's really high, 3% hypertonic saline, okay? This is very rarely used. Like I can't even find a picture of it. Okay, I found a picture of the normal one. I found a picture of the hypo one. I can't even find a picture of the 3% one. Okay, I asked my sister. She has been a nurse for like over 15 years, and she says she never used a 3% before, but it's there. Okay, if you do a Google search, then you will see that sometimes it's used to treat hyponatremia if the person is severely lacking sodium in their system, then you might want to give them some through the IV. It's also used sometimes to treat like, a buildup of brain pressure. But there you have it, okay? That's why it's important to understand, the different types of environment a cell can place in so that you can administer the correct kind of IV. Okay, so for the rest of the class, we will be doing the different types of transport, and there are so many different kinds of transport. Like if I go through the slides, it's going to be overwhelming. You might not be able to remember it, as much or as well as if we draw it out. So that's what we're going to do. Okay, so please take out a new piece of paper. This is going to take us at least like half an hour, okay? So you want to put the paper sideways, and actually I'll just show you what it looks like because I did it yesterday with my other class. Okay, this is what we're drawing. Okay? This whole thing. All right, so we're gonna start here, and then we're gonna split the thing into different categories, and that's the entire note. Okay, so here we go. Here we go. We have transport. Transport across the cell membrane. Okay? Transport across the cell membrane. Hold on, my shapes are not working. Let me try to restart this and see if it's going to come back on. So remember, the cell membrane is selectively permeable, so it's not going to let everything through. So that's why there are different kinds of transport. Okay, transport across the cell membrane. So let's separate this into two categories. Okay, we're gonna start with these ones over here. Okay, so some transport, we call them passive transport. Passive transport. In passive transport, the materials are moving down their concentration gradient. Okay, so this is going from high concentration. Square bracket means concentration, right? We talked about that last time. Going from high concentration to low concentration. Okay, so substances, they are moving down the concentration gradient. Okay, remember, concentration gradient is just talking about the difference in concentration between two areas. Okay, so if you put some food coloring in the water, that food coloring is high concentration compared to elsewhere, which is low concentration. It will naturally spread out, right? So that's passive transport basically. And like I said, this is going to happen spontaneously, so no ATP needed. No ATP needed. All right. We already learned a few different types of passive transport. So let's just go through it. You know what, guys? I think I'll just put this on the side here, maybe, so I can complete the chart. I mean, you don't have to move yours. You probably can't. But I'm just gonna put it there. So passive transport, we have a few different types. Okay. All the hypotonic, hypertonic stuff, that's basically an illustration of osmosis. Osmosis. Okay, I'll give you a definition of osmosis again. Osmosis is basically the diffusion of water. And the key thing to remember is that water moves towards areas with higher solute content. Okay, it's gonna be attracted to the salt. Okay, so we are talking about the movement of water here, not the solute. Okay, so some people say, hey, I thought passive transport is like high to low. How come it's moving towards the higher solute concentration? We're not talking about the solute here. We're talking about the water. Okay, water moves towards an area of higher content. Okay, so for osmosis, the only example is water. And that's the only thing that fits the description of osmosis. And this happens without effort, without ATP. It just does. Okay. Now there is the diffusion that we learned about. That's passive transport. And the kind that we discussed in class, with the food coloring spreading out or like spraying the Febreze and then, the whole class is going to be able to smell it. That is called simple diffusion. Simple diffusion. Okay. Um, so simple diffusion going from high to low, no energy. I'm not going to rewrite that again, but it's ideal for small molecules. Okay, best for small molecules. Okay, and hydrophobic. Remember, the phospholipid bilayer has a thick hydrophobic tail section in the middle. So if other things are hydrophobic, it would interact well with this layer and they would have no problem passing through on their own. So an example of hydrophobic molecule would be like a steroid hormone. Steroid hormone. Okay, so simple diffusion is best for small molecules, hydrophobic molecules, and non-polar molecules as well. Okay, so non-polar molecules like oxygen, CO2, right? They're able to go through. So water, even though it's polar, but it's small enough, so that's why it's going to be able to go through as well. All right, that's that. Does anybody have any questions before I move on? Okay, so to illustrate this, right, like you can draw a quick picture to help yourself see it. Let's say this is the cell membrane. You should be quite familiar with drawing the cell membrane now. Okay, this is outside. This is inside. Sorry, I don't know why I did that. We have to draw more of the cell membrane. And sorry, let me silence my phone. It's my wife. She does not know I'm in class. So we have, let's say we have a bunch of things outside, and then we have some here, right? So these things are small enough, or they might be non-polar or hydrophobic, and they would just be able to move in through the phospholipid layer like that. Okay, that's simple diffusion. It doesn't have to be coming in. Okay, it could be going out. Like you could have I can add a different color here. Like you might have a lot of these blue things, whatever they are, okay, and you don't have a lot of it outside, then the blue will move out. Okay. The movement of one substance is usually not related to the movement of another. Okay, the red will move down its concentration gradient going from high to low, right? Moving in. And the blue, it's going to go down its own concentration gradient. Okay, just because the reds are coming in, it doesn't affect the blue moving out. Because for the blue, if you look at my picture, for the blue, the high concentration is on the inside, right? Maybe I should write this down for you. Okay. So pink is high on the outside and low on the inside. And then for the blue, it is low on the outside and high on the inside. So that's why for the blue, it's going out. And for the pink, it's coming in. Does that make sense to you guys at all? Any questions? All right, so I'll give you a moment to catch up with the drawings and the writing, and I'll tell you more. All right, so far nothing's new. We already learned these things. Simple diffusion, osmosis, we learned on Wednesday. We're just putting it under the category of passive transport because passive transport just happens spontaneously and it doesn't require ATP. So let's see what other type of transport we have. Okay. So simple diffusion is, again, for small hydrophobic nonpolar stuff, but sometimes you will have bigger molecules that cannot cross on their own, or you might have molecules that carries a charge and they cannot cross the membrane on their own. And so we need to use a different kind of passive transport called facilitated diffusion. Okay, to facilitate someone is to help someone. So in facilitated diffusion, it is, I'm going to put it on the side here. In facilitated diffusion, it is the transport. It's still passive transport, okay? It's still no energy required. Transport of materials across, or you can say down, their concentration gradient with the help of a membrane protein. Now remember, on Wednesday, we talked about different functions of membrane proteins, right? Attachment to cytoskeleton, cell signaling, so on and so forth. And one of the 6 functions that we talk about is transport. Membrane proteins participate in transport of material across the cell membrane. There are different kinds of transport that it could do, but in facilitated diffusion, it's it's a type of passive transport. Okay, things are still moving down their concentration gradient. So I have two types of facilitated diffusion for you. Okay. The first kind of facilitated diffusion is called channel protein. Channel protein. The other one is called carrier protein. Okay, so let's focus on channel protein first. Channel protein is used by charged molecules. An example of charged molecules would be, like calcium, okay? Or other type of ions, okay? Calcium 2+. Used by charged molecules. Okay? The protein creates a tunnel for molecules to pass through. Okay? Basically, the charged particles cannot cross the cell membrane on their own because charged stuff is not going to interact well with the hydrophobic tails. Okay, think of the cell membrane as like having this thick layer of oil sandwiched between, right? So anything that's not also oily, anything that's also not lipid-based or nonpolar is not going to be able to cross. So the calcium ion here, they need to rely on the channel proteins. So I'm just going to draw it out for you to help you understand a little bit better. You guys will be expert in drawing the cell membrane by now. And here is a channel protein. Right? It's an integral protein that goes all the way through. And then we're going to put a tunnel in the middle. A channel is like, basically it means a tunnel, okay? So let's say we have a lot of calcium on the inside. Okay, so these are like charged. Doesn't have to be calcium, could be other things, okay? But it's charged and it's high over here, high concentration. and then it's low concentration on the outside. Right? So what happens is they will go through the tunnel and move to the lower concentration. It's same concept as simple diffusion, but with the help of a protein. Okay. Over here, for carrier protein, it is used by large molecules. Large molecules such as glucose. So we can say a molecule binds to the carrier protein and the carrier protein changes its shape. Changes shape as it moves the molecule across the membrane. Okay, I'll explain. Just copy it down first. Okay, so it's like one of these revolving doors. Okay, as opposed to the channel protein. Channel protein is just like, it's just a tunnel you walk right through. But for these revolving doors, like at the mall sometimes, right? Like you have to go into the door and you push and the door rotates and then you are going to be inside. So in this analogy, the rotating door is the carrier protein and you moving through it is going to be the particles. Okay, so let me write it out, draw it out for you. Again, we will draw the lovely, lovely plasma membrane. Okay. Remember the tails are the hydrophobic stuff, right? So we have our carrier protein here. This is the channel protein. This is the carrier protein. And let's say we have some of these triangle stuff that we want to move through, okay? And there are a lot of them outside and not a lot on the inside. So this is high, this is low. All right, so what happens is, I can't really show you this in virtually, but try to visualize it with me, okay? This triangle, it's gonna bind to the protein, and then it's gonna cause the protein to shift, to change its shape. After it changes its shape, then it will be facing inside, and then it will spit it out. Okay, so just like the revolving door. The shape changes, the protein shape, not the molecule that you're moving, okay? That doesn't change. The triangles don't change shape. What changes shape, what changes conformation is the carrier protein. Okay, so binds to the protein, causes it to change, and then now it spits it out, and then it goes back to the original shape, grab more, and on it goes. No ATP required. Why? Because it's going from high to low concentration. It's passive transport. That's all the passive transport that we have. Does anybody have any question at all? Okay. So next we're gonna do active transport, right? Active transport, which is we transport is up here, passive transport, and then we're gonna go over here. And we are going to do this. Oops. I'm gonna have the active transport now. So for active transport, it is going uphill. It's like pushing a boulder up a hill. That's gonna need some energy, right? Imagine a hill and then there's a big boulder, big rock, and you're pushing it up. That's active transport. And so it's going from low concentration to high concentration. And you are going against, okay, moving against concentration gradient. ATP needed. Okay. So I'm going to show you a few examples here for active transport. Okay, now I'm just showing you ahead of time. We're gonna have an example here. We're gonna have another thing here. This thing's gonna have two things, okay? And then of the two things, this thing's gonna have three things, okay? So if you're planning for space, that's what we have to do, okay? All right, let's do this guy first. We're gonna have protein pump. Protein pump. So protein pump basically is, now it's gonna sound very similar to facilitated diffusion, right? Facilitated diffusion is transport of material down their concentration with the help of a membrane protein. But for protein pump, it's also membrane protein, but is transport of materials against their concentration gradient with the help of membrane protein. Okay. So I have two examples for you. Okay. Okay. These are just examples. Like they are not like different categories. Okay. So example one, it is called a proton pump. Proton is H plus. Okay. Proton pump. Does anybody know which part of your body has acid? Which organ contains acid? The stomach, that's right. Thank you, Angela. So the stomach has acid, and what makes the acid acidic is basically H plus. Okay, so here I'll draw a stomach for you. Oops. Okay, so that's what a stomach looks like. Now, if you look at the walls of the stomach, which is made up of cells, right, basically, and on the membrane of those cells, you will have these proton pumps. Okay, proton pumps. And the job of the proton pump is basically to keep on adding H plus to the acid. Right? So basically they keep on adding H plus. You already have quite a bit of H plus in the stomach. Okay, so it's already like high concentration of H plus. But the pump will keep on adding more to it to keep it acidic, right? To keep the pH low. So that's a type of active transport. People who have heartburn, they have to take they can take Tums, but then like for more severe cases, they will have to take proton pump inhibitor, okay, PPI. Okay, so proton pump inhibitor would inhibit these pumps to reduce the amount of H plus in the acid, and it helps with the heartburn. Okay, so that's a first example. I will give you another example here. Okay. Like I know it's a lot of details, right? But don't worry, I will give you another review video for the test, so you will know what to focus on when you're studying. Okay, like I always give you more details than you need to know. Um, it's better to learn it and not have to memorize it for the test. Then later on when you move on to some other program, you're like, oh, I never heard of this before. So this is called sodium potassium pump. We will talk more about this next semester, but a lot of cells have the sodium potassium pump, especially in the neurons, okay? And what it does is this. Right? Let me try to draw it out for you. Okay, so by now you should know what that is. That is the cell membrane. Okay, now this next one might be a little bit tricky to draw, but basically I'm gonna have three square slots on one side, and I'm gonna have two like semicircle slot on the other side, okay? So this purple thing here, this is called the sodium potassium pump. And as the name implies, you'll be pumping sodium and potassium. Okay. So the potassium is going to be represented by these circles. And then the sodium will be represented by these squares. So one side of the protein will fit the sodium, the other side will fit the potassium. Your cell actually does not want too much sodium in the cell, in the cytoplasm. So it's going to pump it out. And this is outside. This is inside. But it likes potassium. Right? So it's going to bring the potassium in. Okay. And the way that the pump works is for every 3 sodium that gets sent out, you're going to be bringing 2 of them in. Okay. For every 3 that you send out, you're going to be bringing 2 in. Okay. So if you keep on doing this, if you keep on pumping sodium out, then it's going to be high concentration of sodium outside and low concentration of sodium on the inside. So you see, this is active transport. You are pumping it from low to high, right? All those sodium actually wants to come back in, right? But they can't, okay? Because the barrier blocks the membrane blocks charged particles, right? So the pump keeps on sending more and more sodium out. Similarly, if you keep on bringing potassium in, you will have low potassium on the outside and high potassium on the inside. And this process of continuously transporting both of these things against their concentration gradient requires ATP. We good? You probably need a moment to, jot that down. For every 2 potassium it brings in, you know what? Let's write it better. Every 2 potassium is exchanged, are exchanged. Every 2 potassium in that you brought in are exchanged with 3 sodium out. You don't have to memorize the numbers. Okay? I'm just putting it there for completion. Okay. Almost there. Almost there. Another kind of active transport is called bulk transport. Okay. So bulk means a lot. Okay. So bulk transport is moving large quantity of substances across the membrane. Or moving a very large particle across the membrane. Either you are moving a lot of something or you are moving something that's really big. Both are called bulk transport. If something is bulky, it's really big, right? Right. People go to Costco and they buy things in bulk. That means they buy a lot of it, right? So both examples here would be considered as bulk transport. So for bulk transport, we have two types. Okay. Sorry, the chart is getting really messy now. Okay, let's do this type first. This is called endo. Oh, no, 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 no. Let's do exo first. This is called exocytosis. Exocytosis. Exocytosis is sending things, and again, because it's under bulk transport, when I say things, I'm talking about like a lot of it or like really big stuff. Okay, so sending things out of the cell. Sending things out of the cell. So, we actually already learned about an example of this. I will draw it for you, okay? Maybe watch first and then draw because you don't know what I'm drawing and it's hard for you to follow. So let's say this is the cell membrane. Just watch, okay? This is the cell membrane. And we have a vesicle here. The vesicle is freshly repackaged from the Golgi body. And it had some proteins in it. In class, I told you that these vesicles can go to different places, right? It might stay in the cytoplasm until later. It might, become part of the membrane, or it might go and become a lysosome, or you can release it out of the cell. So the vesicle will move towards the edge to the cell membrane, and it's going to touch the membrane. It's going to touch the membrane. And after it touches the membrane, it's actually going to start fusing with the membrane. It's going to start fusing with the membrane. Okay, and eventually it will become part of the membrane, the vesicle. Okay? And then the content, whatever was inside the vesicle, they're going to come out now. Right? Because we are releasing a lot of it at the same time. This is called exocytosis. The cell is expelling something, sending a lot of it out. Okay? Give you like 2 minutes to catch up, draw whatever you need, copy it down, ask questions. Okay. The other um, type of bulk transport is endocytosis. Opposite of exo is endo. So in endocytosis, instead of sending things out of the cell, you're bringing them in. Bringing things, really big things, or a lot of something into the cell. And I'm really sorry, but there are three types, okay? There are three types. Actually, you know what? You don't really have to draw this again, uh, like now, but you can draw it later, okay, when you are cleaning up your notes. Endocytosis is basically the same thing, but now is going to be going in the other way, okay? So there are some particles that you want to bring into the cell, right? So they will move to the cell membrane and cause the cell membrane to kind of cave in, and eventually it will close off into a bubble and form a vesicle. That's basically endocytosis. It's the opposite of exocytosis. Okay, so you can draw that later. Um, but there are three types of endocytosis that I want to quickly mention. And then we are done, okay? Just hang in there. First one is phagocytosis. Phagocytosis. So phagocytosis means, like if you translate it, these are based on, again, like Latin and Greek, right? So if you translate it, this is called cell eating. Cell eating. So not all cells eat. Okay? Only some are able to do this. An example of that would be like a white blood cell. Okay? Or WBC, white blood cell. So let's say there is a bacterium. Bacterium is singular for bacteria. And your white cell is gonna see the bacterium and it's like, oh, it does not have the same ID tag as the rest of the cells in the body. That means it does not belong here. Right? And so what happens is the white cells will actually go surround the bacterium. Okay? It's like that game, right? A Pac-Man. You guys know Pac-Man? Like the yellow guy that goes around and eat the dots, right? It's literally like that. And then what's going to happen is it will eventually swallow the entire bacterium. All right. Who remembers which organelle will come and break down the ingested bacterium now? Which organelle will help digest and break down the bacteria? Anybody? The lysosome, okay? Lysosome contains digestive enzymes and is going to come and break it down, okay? So that's an example of phagocytosis because the cell is eating something big, something bulky. Now, if there are cell eating, then you guessed it, there must be cell drinking as well, which is penocytosis. Penocytosis. Right? If you translate this, it means cell drinking. Okay, I'll just give you an example. Um, the human egg can bring in fluid, fluid from its surrounding to obtain nutrients. Okay. So you're bringing in just primarily liquid. That's why it's called cell drinking. Penocytosis. And last one. Okay, thank goodness. It's the receptor mediated. Receptor mediated endocytosis. It's a very long name. It's a mouthful. Um, I will show you. I'll draw it for you first because as soon as you see it, you will understand it, and then I can explain to you more. So this again is the cell membrane, and on the surface of the cell membrane, we have some receptors. Okay, this is a little bit it's similar to the signaling receptor that we talked about before, but it's also a little bit different. Okay, so let's say we have some receptor here. And we have different kinds of molecules in the environment. And let's say we have these circle ones, and then maybe we have the blue triangles and whatnot. Okay, let's just throw in a third kind here. Let's just have some purple stars or something. Okay, I don't know. Whatever, it doesn't matter. All right. So in order to move some of these things in, they need to fit in the receptor. Right? So only molecules or particles that can fit in the receptor will be allowed into the cell. This is receptor. Okay, protein receptor. The star cannot come in. The triangle cannot come in because they don't fit, right? Only the circles will be able to come in. It's like the this toy here. Hold on, I just gotta grab the image to show you. You know, this toy. I feel like I talked about this in class already, but I forgot if it's your class or some other class. It's all a blur. It's like the shape sorter, right? Like each slot is a particular shape. Only if it fits the shape, then it can go into the box, right? So only if it fits the receptor shape will it be allowed to cross the cell membrane. So receptor-mediated endocytosis, it is more selective compare compared to other kinds of transport. Okay, only materials, substances, molecules, whatever we're going to call them. Okay, only things that fit the receptor will be able to cross the membrane. All right, that's it. That's all the different kinds. All right. None of this stuff is going to be on your quiz number two. Quiz two is only second half of lecture two and all of number three. So focus on preparing for that yet. The quiz, of course, is next Friday, done online. All the information is on eCentennial. Now, this is a really big chart. So I think it's a good idea to maybe redraw it when you have time, just like reorganize it a little bit. I'll of course post this online for you to for reference. Now, before you go though, I have one other thing I need to talk to you about. This is important for your lab. Uh, Speaking about the lab, I just posted the lab this morning. If you go on eCentennial, there is the beetroot experiment. There is the procedure. I will give you the procedure next week. Okay, I'll print it out for you, so you don't have to print it out. Okay, but you can start looking at it if you have time. Okay, like I said, you need to know what the procedures are before coming to the lab, right? You need to know what kind of instruments you'll be using and what kind of steps you need to be doing. All right, so start reviewing that. And also, there will be the lab report. The lab report is separate from the procedure. This is the one that you'll be handing it in to me. Okay. So I need a physical copy in class. Okay. I will I will give you one to fill in class, but like I expect you to type out your answers, right? Okay, I'll tell you more about this later on, but start reading the procedure. Now, one of the questions in the by the way, there are a lot of conceptual questions here. I'll post the answer for you to do it to check, okay? We're not going to do it now. One of the questions in the lab report requires you to understand this concept here. I mean, we don't have a lot of people here right now, but let's do a poll. If you see the poll, then choose something. If you don't see the poll, you can type the answer in the chat box. Okay, but I want you to think about this question. and then I'm going to explain it to you. Okay, so give you like a minute to think about it. Okay, well, not much action going on here this morning, but for those of you who chose something, a lot of you chose A. Okay, and I think it's because you see the word hypotonic, right? You see the hypotonic solution, and you remember in class we said, oh, hypotonic means the cell's going to get big and burst, right? But this is a trick question, and here is why. If you just put an animal cell in a hypotonic solution, yes, it will swell and burst. However, the question says, after freezing and thawing the animal cells, right? So that's actually going to change the cell. Can you tell me, anyone can tell me, please, what happens if you put water in the freezer? Like it turns into ice. Yes, I know that. Okay. But like, what about the volume of the water? Like, how's that going to change? If you filled up a water bottle and you with water and you freeze it, what happens to the volume? You guys know the answer, right? Don't you? You've done this before. Isn't the volume the same? Oh, Fatima, you gotta freeze some water right after this class and make some observations. Anyone else? What happens if you freeze water? What happens to its volume? No? Well, if you don't know, it's gonna expand. Okay? You can fill up a water bottle, you put it in the freezer, and afterwards you see that it got bigger. So as water freezes, it expands. And that expansion is actually going to pop your cell. Okay. Also, there is going to be like ice crystals that are forming that would pierce the cell membrane. Okay. Because the cell is mostly water inside, right? The cytoplasm. So after freezing it and thawing it, your cell is actually full of holes. It's dead. Okay. So if it's full of holes, then it doesn't matter whether you put it in hypotonic, hypertonic solution. There's no more, you know, regulation of any kind. The water just move in and out equally because it's broken, right? The cell membrane is broken. So that's why the cell is not going to change the size. Okay, keep this in mind when you are doing your lab. Right? There is one question at the end that requires you to think a little bit, and if you're stuck, come back to this concept check question, think about what I've said, and apply it to that question. Okay. All right, that's it. Thank you so much for taking the time to come this morning outside of our regular schedule. I hope it has been useful. And no class on Monday, remember. I will be seeing you in class on Wednesday. Take care, guys. Enjoy your weekend. Bye for now.